Dmitri, and
all right, thank you. So I would add several more things about the equivalentization. So let's start with the category C, which is non-degenerate braided fusion. We take it for simplicity. Many things can be done when it's degenerate. So let E be a Tannakian subcategory. Inside C, we have an algebra of functions associated to this subcategory, so complex valued functions on the group G. So this is a commutative separable algebra. A modules in C, and this will be a fusion. Or we can take A modules inside the centralizer of E, and that's a braided fusion category. So what we have a braided category sitting inside a fusion category. So let's try to understand the relation between the two. So I'm going to list some related things. So first of all, there is a faithful G grading on this large category, on the category of A modules in C. So I will write this as a sum of homogeneous components. So grading on the fusion category means its decomposition such that the tensor product respects the group multiplication, right? So the x and y component, when the tensor, you get x y component. Okay, so here, so let me explain where the grading comes from. So here the G homogeneous component of this graded consists of modules M that satisfy this twisted condition. So let me write this down. So you have algebra A module M. You can apply square braiding between them, and then here you can have like module action. And here you twist the module action. Remember, this algebra A that we constructed, it has an action of G by translations. And this action transfers to the action on module. So you can apply here a G inverse tensor identity, and then apply the module action. So the fact is that such every simple module would fall into one of such components, and you have a gradient defined by this. So this is one piece of structure. But incidentally, here the trivial component of this gradient is this category, is the braided category. So I should write it here. Anyways, so this is CA identity. Next, that's not all. So not only it sits there as a trivial component of the grading, but it's also central in the following sense. So there is an embedding of this trivial component into the center of CA. So you see it's braided. So and that the fact that it's embedded into CA, it's embedding into CA factors through the braided embedding now into the center, like this. In other words, this factors through the central to the braided functor to the center. Finally, there is an action, and some of these things I mentioned yesterday. There is an action of G on RCA, again, that coming from the action on A, on the function algebra. Such that, see, once there is an action, there is an equivalentization. So you can take equivalentization, and equivalentization is equivalent to C as a braided category. So, so what is now? Sometimes you would see in the literature the notion of a G-crossed category, and it's a long definition which I'm not going to give. But what I try to do is to unfold this definition in kind of the simplest possible terms. Okay. Now, what is perhaps not so straightforward here is the following. So this category CA is just a fusion category. But when we take equivalentization, we get a braided category. All right. Now, this is due to the fact that all these gadgets, that I mentioned, the grading, the action, the central embedding, they combine together to show that this equivalentization has a braiding, although the original category does not. So let me give you an illustration of this. So, in fact, like the simplest illustration. So we take C to be the center of G-graded vector spaces. Let's take E to be rep G sitting inside here. Then, well, you can do all these things that we did in general. So in this case, CA, well, in this case, first of all, EA will be what? So this will be the category of vector spaces, right? So we mod out by rep G, you get a category of vector spaces, and CA is vec G. So now this is of course naturally graded. That's by definition the category of G-graded vector spaces. So furthermore, there is this thing that I mentioned that the center of this category is precisely the equivalentization of them. And somebody pointed, that this category is not braided, but we still take equivalentization. That's right. Because the equivalentization we take is with respect to conjugation, right? And to say something, that something commutes with conjugation, it means that something has a central structure, right? So that's where a braiding comes from. Any questions about this?
I have a really dumb question, Dmitri. So in the diagram up above,
yeah,
we're really just writing down well, definition of the twisted module, right? You're just twisting by G inverse.
That's right.
So why do we need the double braiding across the top? Am I dumb, or is that just
no, that's not dumb at all. But I mean, let me put it this way. So what happens if there is no twist? Okay, then what we have are so-called local modules. Okay, so that modules that are compatible, with the square braiding. Well, that's precisely what EA is. Okay, so you cannot really drop this condition. Like if you just have equality here, then there is no diagram you can draw. So yeah, I'm not sure this is the best way to explain it.
Okay, so it's you're saying basically this is an analog of
it is, yes, it's kind of twisted version of a local module.
Right, so we need the braiding and okay.
Yeah.
All right.
I want to ask an actually dumb question. Way back when you wrote down your setup, A is functions from G into C.
Yeah.
Well,
this is
how is that in your category C?
Okay, so this is a representation of G, agree? Because G acts on this algebra by right translations. So this function algebra sits inside rep G with the usual action by translations. Okay. And this inside C.
Yes.
All right. And so we view it as an algebra of C because that's where we're going to take modules, right? Now, to take in modules in rep G is not very interesting. You just get vector spaces. So we take it in the larger category. Okay. So so next I'll ask this question. So how to recover? Let me just mention something else. So yes. So how to recover braided category from its core? So let me remind how we defined core yesterday. So if E inside C is maximal Tannakian, then E prime A, which we denote core of C, is independent of the choice of E, so doesn't depend on the choice of E. And in particular, you see, like if E is real G, there can be different Anakian categories with different underlying groups. I'll show you an example. So if C is non-degenerate, then so is its core. And furthermore, the core carries an action. So there is an action of G by Braided after equivalences of the core. And now this thing is not canonical because, like I said, there can be different groups, corresponding to different Anakian categories. But what is canonical? So the image of this in the automorphism group is canonical. Now, to illustrate, I'm going to put this up. Now, to illustrate the kind of problem we are trying to solve, let us consider the simplest example. So what if core of C is trivial, the category of vector space, the smallest possible? So what can we say about our category then? Well, in this case, we need the category E, the Anakian category by which we do this deequivalentization. Well, it must coincide with its centralizer, right? Because if it's strictly less, then there will be some non-trivial modules. So this is what we call a Lagrangian category of C. So I mean, again, the analogy is that it's analogous to the largest isotropic subspace of a space with an inner product. So now in this case, E prime A is trivial, but remember this is the trivial component of the graded category. So C prime A, well, it's graded, and the trivial component is vector spaces. So it's pointed. So must be pointed. Because like here, like if you over here, if you have homogeneous component one-dimensional, that's so is every other component, right? So all objects are invertible, you get a pointed category. And furthermore, so the equivalentization of this, there is no prime, the equivalentization of this is equivalent to C, but then we also know that the equivalentization of this, that was a question I answered yesterday, is precisely the center of this category, which is also known as the twisted Drinfeld double. These are just different names of the same thing. So twisted Drinfeld double corresponding to some omega, a third cohomology class. So there, we solve this problem. So the categories with the trivial core are precisely these categories, the twisted Drinfeld doubles. Okay, so this problem, in fact, has quite a few solutions, right? So how to summarize this? So let me just so conclusion that we derive from this. I mean, it's of independent interest, right? So C is equivalent to the representation category of the twisted double if and only if the core of C is trivial, if and only if C contains Lagrangian Anakian subcategory. All right? So this is the simplest instance of the problem that I outlined. But any questions about this? Say again?
It's showing the maximal, right?
I'm doing what?
It's showing the maximal. Do you import the maximality? No.
Maximal? Well, if C is non-degenerate and E satisfies this, then it is maximal. It cannot be larger than that. Okay, so but now what's still still opens now, but what about the general case? So what happens in general? So let's see, let me state this precisely. So let's say, so given say a non-degenerate braided category D with an action of group G by braided at equivalences of D. So can we recover non-degenerate C with Tanakian subcategory inside it, such that this result of this de-equivalentization is D. Okay, so in other words, can we reverse the steps in this construction, right? So here we started with C and rep G sitting inside, and we produce this thing, right? Which, if we choose E to be maximal, is a core, right? Now, can we go back? So suppose we have a tensor, non-degenerate braided tensor category with an action. So can we enlarge it to get the D in this fashion? Such a procedure is called gauging. And I'm sure there are like contexts, in other areas that refer to this. Yes? But I hope that the problem is clear, right? So this was the previous example, was the solution of the gauging problem for the trivial case. So this, in fact, well, the answer to this is that this is possible sometimes. There are certain abstractions, okay? But, what perhaps is more important, and there is an interesting theory behind this. So, so let me be more precise of what we want. After all, like, in order to reverse this process, we need to get a graded category at some point, right? Okay, so let me restate this. So we want, so more precisely, we want a graded extension, a G-graded extension, a faithful G-graded extension of D. I'll use letter B for this, such that the properties that I outlined in the beginning of the lecture would hold true for this extension, such that the trivial component is D, and this trivial component is embedded into the center of, and furthermore, and an action of G on B, right? That's also what we had, right? This category is acted upon by the group G, and an action of G on B such that the equivalentization is braided. Again, non-degenerate braided. So again, I did not do anything new. I just tried to reverse the steps, that were taken, when we constructed this, the core of the category. Okay, well, this would require like some new techniques. And I have to introduce a new notion, that of a module category. So a module category over, let's say, a fusion category. I use the word D for the fusion category, right? Or a fusion category D is, well, it's a category M, satisfying all those things that we usually require, abelian, C-linear, along with D. By functor, the action, module action, associativity constraints satisfying certain coherence. It's clear what we should require, right? Like the module, the usual module action of a ring on a module is required to be associative, or here it's associative up to isomorphism. This isomorphism is to satisfy something else. Well, that's a very natural notion, right? Because we don't study rings in isolation. We study them through their modules. Similarly, we study tensor categories through their module categories. Now, if this D is braided, then we can tensor the module categories. Similarly, how we can tensor modules over a commutative algebra. So there is this operation, which would require, of course, its definition, but I hope it's kind of intuitively clear what it should be. So tensor product over D of module categories N and N. The easiest way to do it, without like going to too much abstraction is just to take tensor product of algebras, okay, and introduce like the algebra structure on a tensor product. If the category is braided, this is possible. Now, if this is there, then we can talk about invertible module categories. So before we do this, now what kind of the structure we get in this way? So we get put it like in both phase. So the modules over D. So let's see, objects are module categories, morphisms are functors, module functors between them, and there are also natural isomorphisms between those. So this is a tensor two categories. Again, I'm not going to use much of higher category theory, but I need to call things by their proper names. So, like I said, we can talk about invertible the module categories. Meaning what? Well, with respect to this tensor product, there is always, of course, identity, the regular category. So the unit is D, the regular to module. D acts on itself by multiplication. So then invertible module categories are those that for which there is the inverse with respect to this. So these are precisely invertible part of D, and it's called the Picard group of D. So what that is, it's a two categorical group. So we know, of course, what usual groups are, right? We have seen yesterday, I think, a categorical group, the group of equivalences, right? And so this is kind of the next layer. You know, that's everything is invertible, but there are two layers of morphisms. Okay, so now how is this related to the question at hand? So here, if you look at this decomposition, then of course you observe that the homogeneous components here, let me refer to this as star. Creating messes. All right. So that homogeneous components are in star are D module categories, right? Indeed, that the trivial component acts on each homogeneous component by means of tensor multiplication, right? In fact, they are invertible. And so what we furthermore, the tensor product of this graded category, it should map BG, BH to BGH. This gives rise to, okay, by the usual algebra like techniques, you know, like this is kind of compatible with the multiplication by D, by the trivial component. This gives rise to the functor between the product of these categories. And this is in fact an equivalence. So what this amounts to is that, to put it in a concise form, that what we have is a monoidal two functor from G to the Picard group. So again, I will try to denote the higher structure by both phases, the Picard group of D. Again, this is like a short sentence, but there are kind of lots of things, you know, that are hidden in this definition, right? You know, well, this is precisely what is needed to allow to make sure that, you know, the result is a tensor category. Okay, so now, well, there is a converse to this statement. So conversely, there is a theorem that tells you that you can go from such a functor to an extension. So given a monoidal two functor from G to this Picard group of D, let's give it notation, say G goes to BG. So there is a the direct sum of this thing is a tensor category, is a fusion category with which is a degraded extension of there. So that's well, and let me make before I continue, any questions about this? Well, so here we view G as a discrete two categorical group. So objects are G, the only morphisms are identities. Okay, so this is the thing. So this is kind of the concise way to express this. But let me also mention something. So remember, I said that on top of this, we need an action of a group G here. Okay, well, there is such an action because what we have here, let's see. So the homogeneous component Bx is equivalent to D-module functors from let's see from let's say Bg to be Xg. So how is this equivalence given? Well, we pick an object here and we have a left multiplication by this object, right? So homogeneous object in component X tensors with the object in component G gives you a object in the component Xg. Yes.
In the theorem, B is braided.
I where braided.
So
I'm sorry.
in the theorem, on the right hand side, B is braided.
D is braided, yes. Yes, I mean, otherwise you are not able to talk about the Picard group, right? In order to tensor module categories, one-sided module categories, you need a braiding on the category. Okay, so but now this is also equivalent. Let's see how else we can go from G to this. We can go by means of the right multiplication, right? So let's see. So if you multiply G by G inverse X G, right, we will get there as well. Yeah. So this is the same, therefore, as B G inverse X G, and this would be by means of right multiplication. So we play left against right multiplication, right? So now it's significant that we again go from X to its conjugate, and we call this, I know, Fg. So we have this equivalence between the homogeneous components Bx and Bg inverse Xg, and this can be extended to well, I guess I have to put X. So we extend this by linearity, you know, from a homogeneous component to their sum, to Fg from B to B, and this is the action of the group G that we were looking for. All right, now this sounds fairly abstract, right? You know, all of a sudden we are dealing with this new gadgets, higher category. So let's try to make it a little bit more down to earth. So first of all, there is a way to describe this Picard group. So there is a theorem that tells you that there is an equivalence between the Picard group of B and the group of braided autoequivalences of B. So where B is non-degenerate. So, well, let me, before I can actually outline the proof, but let me specify what kind of equivalence is this. So this is a one categorical group, right? There are the equivalences, there are morphisms between them. There is nothing else, right? There are only this. Well, this is, I just said, it's a two categorical group, right? So the only meaningful way to talk about equivalence is to consider a truncation of this. Truncation, so that this is now is a one category. That's how we compare those. And the way this is established, I think, is quite nice. Yeah, yeah, go ahead.
Can I ask what that?
So, okay, so now we replace each one morphism by its equivalence class. Make sense? So, you know, so two morphisms disappear. Right, so for instance, what the truncation of a one categorical group? The underlying group of objects, yes, where all the morphisms are gone. So here all two morphisms are gone. Okay, so the way this works is the following. So given an invertible bimodal category, we have two equivalences. So we have equivalence between B and bimodal endomorphisms of M. Again, think about ring theory, right? If you have a commutative ring, right, then the left multiplication by objects in this ring is endomorphism of a module, right? It would commute with a module action. Yes. So what we do, we just send here X to the left multiplication by X. And our job is, of course, to permute this thing with the bimodal action on M. Well, this can be done because there is a braiding, right? So this module structure given by the braiding. But you see, we did mention this earlier, that braidings come in pairs. Along with every braiding, there is its reverse, right? So we can do an equally good thing by considering the same functor, but now with the module structure. So this is braiding. Defined by the reverse braiding. You see, if your category is where do you go? So here, if your category is non-degenerate, then the braiding and its reverse are quite different. Okay, because it's very far from being symmetric. So I call this alpha plus M, and this alpha minus M. So both are equivalences, thanks to M being invertible. So if I compose one with the inverse of another, let's say I apply alpha plus first, and then inverse of the other. What I get is an equivalence from B to B, which turns out to be a braided anti-equivalence of B. So this is a braided anti-equivalence of B. All right. So, so where did we go? We went from M to braided anti-equivalence. Let's give this a name, like D. Okay. So we constructed an assignment that goes from M to dm. This assignment over complex numbers is an equivalence. All right. Again, proving this would require some work, but at least I gave the definition. Now, why is this useful? Because this group is much easier to describe, right? Well, there is still some work, but for example, we know this can be described more or less explicitly. We haven't seen some examples last time, right? So for the pointed category, this is just the orthogonal group. Well, orthogonal groups are also fairly complicated, but at least we know what they are. Okay, so all right. So now back to our problem, right? So we figured out that in order to do this gauging, to recover the large category from its core, for instance, we need to produce, where is it? Like this monoidal two-functor, right? So let's do this in a kind of a more pedestrian way, because it's kind of hard to come up with monoidal two-functor right away. Instead, remember the setup that was given to us. So the setup was non-degenerate D with action G by braided anti-equivalence. But we have just seen that this group of braided anti-equivalences is isomorphic to the truncation of the APK group of D, right? So this is one categorical. So we do have, what we have is not a monoidal two-functor, a monoidal, just a honest monoidal. You see, this is given to us. That's what we start with. And the problem now is, can we upgrade this monoidal functor to a monoidal two-functor, right? But remember the things that we cut from the Picard. So can we upgrade this to a monoidal two-functor? Look, I'm not really a big fan, of this higher abstraction. I only use them, when it's necessary. Okay, and here it's necessary because you cannot really, whatever you say will be just a rephrasing of this thing. And as it happens, the answer is that not always. So not always, because there are homological abstractions. There are abstractions. There is an abstraction And rather than defining this abstraction, I can tell you where it lives and why it lives there. So this abstraction lives in the fourth cohomology group of G with coefficients in the multiplicative group of complex numbers. And if this abstraction vanishes, so there is a usual principle, right? You know, like if when such an abstraction vanishes, then the solutions are parameterized by the third cohomology, by the cohomology class of 1 degree lower, right? We have actually seen this. I think it's already gone from the board. But remember, we recovered like from Vect all these twisted Greenfield doubles. And it was significant that it's not just a single Greenfield double, by the whole family of them, where omega is a third cohomology class. So it wasn't a coincidence, okay? Because like in this case, if abstraction vanishes, then such functors are parameterized by H3, by the third cohomology group, just like they are here. Okay, because you can also, you know, express this in terms of a monoidal two functors. Well, this will be a little bit silly because the Picard group of this is a trivial group, right? So we should not really, you know, bother with that. Okay, and it's also I can also explain, you know, how this parameterized. Well, I should say not by this, by a torsor of this group.
Does this obstruction in H4 correspond to the pentagonator in the monoidal two category of like the
It is, yes.
Okay.
That's yeah. So the appearance of the fourth cohomology is natural. You see, like in monoidal one category, like you deal like with triples of objects, right? And you know the kind of the highest axiom you see is the pentagon. In monoidal two category, well, the coherence will be in terms of four objects, okay? And instead, the kind of the diagrams that you draw on a plane will be replaced by this cute polytopes, okay? Just imagine gluing together several pentagons and forming, you know, some, you know, it's a very cute thing. You should look it up. It's called associahedra, okay? Anyways, yeah, so the relevant cohomology group is H4. So let me explain, like in terms of the braiding here. Look. If you have such a category, and suppose you already constructed one such category, say that abstraction vanished, and you managed to construct one thing like this. But then there is, of course, a thing that you can do. So remember how we went from vect G to vect omega G, right? Where omega is a Ricard cycle. We just twisted the associativity a little bit, right? We can do the same thing here. So we can just take new associativity on homogeneous objects like XF, XH, XG to be the old associativity times this Ricard cycle. The value of this Ricard cycle on the homogeneous, you know, on degrees of homogeneous components. So, and again, you know, the only thing that is required from this, in order for this to work, it has to be a Ricard cycle. I mean, up to cohomology, right? So that's the appearance of this H3. Why the solution is not unique? Okay. Old, right? So the old associativity, like, you know, this came with its own associativity, right?
FGH.
On the left-hand side.
FGH. Okay, yeah, I said not very good with alphabet. FG, FGH, FG. Yeah. Okay. Yeah, so you know, this was the kind of the original thing that was present here. This was like a new thing that was that we construct by means of this torsor. Any questions?
I have another question about some earlier stuff. So like you had provided two processes of going from functors from G into the Picard group and faithful G graded extensions of D, right?
Oh, Well, that's just like one thing, that's like, this two factor is what it takes to construct such an extension.
Right, yeah, so, but both of these objects form at the very least like categories. So do these two processes provide an equivalence
Yeah.
of categories or?
Yeah, you can state it in a more kind of, intelligent way. Yes. So they form like at least groupoids, right? So you can say that the groupoid of such extensions, of G-graded extensions, is equivalent to a groupoid of such factors. And it's probably more than just a groupoid. I think it's like one
Like
group,
two groupoids.
something like this. Yeah,
Okay.
it's an equivalence of groupoids, of course. Yeah.
All right.
Yeah, I'm just trying to keep things down to earth because, I don't know if people came here to hear about higher categories or lower categories. I'm trying to keep, the ground. All right. Okay, then, so this kind of completes like this part of the theory. I explained how to do this, but well, the next thing I'm going to discuss, so maybe I'll just outline it today and then continue tomorrow.
Dmitri, before you start, could I ask another stupid
Yes,
question?
but
Why-
don't call them stupid. You can ask questions, but
I will ask a question which may or may not be stupid. Why are we interested in this Picard group? I mean, this is the invertible objects in this
well, I mean, I guess that is what I said. I hope it's one of the reasons, like because it's a natural problem to construct. That's how it was discovered, more or less. Like people wanted to produce such extension. They wanted to see like what corresponds to them. So it turns out like this Picard group, and it's, and again, this theorem that I proved tells you that's not something unusual. That's really kind of the categorical orthogonal group, the group of symmetries of a given
So if we know
non-degenerate category. Yes.
sorry, if we know the Picard group, are we able to classify all the extensions of the module category?
Well, it depends, like, what you mean by, if you know just underlying group, then no, but because we need like morphisms between them and so on, okay? So, well, at least if we know, like, it as a one categorical group, right? And there is kind of a procedure, but, you would face this abstraction at the end, well, like sometimes one can compute, sometimes it vanishes. For instance, if G is cyclic, then this is 0. Right, and so and then there are no abstractions to doing this. But again, it's really the group of symmetries of an categorical structure that we care about. So I think it makes sense to study those. All right, so let me then advertise briefly what we will do on Friday. That will be last my lecture. So next there will be the categorical with equivalence. And the reason for this, the motivation is very simple. You see, like, so you can, of course, like state this problem, about possibly classifying all non-degenerate or modular, which is the same more or less, tensor categories, braided tensor categories. Well, that's a hopeless problem, okay? One should not ask this question because there is no like possible answer to this, okay? So what we can hope for is to classify them up to something, okay? So we want to classify them rather than classifying them on the nose. Is this the right expression, on the nose?
Yeah.
Yeah, okay. So then we want to classify to do this up to some equivalence. Up to some equivalence relation. This is done. Well, we're going to think of certain braided categories kind of trivial. Whatever, I mean, it does not really, it's not meant to insult them, but just to make our life easier. So what we will do to get this equivalence relation, you see, like, what's the kind of one of the first examples that we have seen of braided categories, the centers, right? You can compute the Drinfeld center of a fusion category. That's a huge class of categories, right? Because classifying Drinfeld centers would involve, in particular, kind of classifying all fusion categories up to Morita equivalence. This is a hopeless problem. So we will mod out, and I will have to explain what this means by Drinfeld centers. So some braided tensor categories are Drinfeld centers. They will begin in this classification. Some are not. Okay, so it turns out that what remains after this modding out by Drinfeld center by Greenfield centers is still a lot. Okay. And like the result is actually has a group structure called a categorical with group. And one can prove some results about this group and state some conjectures about the generators of this group. All right. Again, so this is just to make sure that you show up tomorrow after the hurricane or whatever is going to happen. Yeah, I think that's I'm done. Yes.
Time for more questions.
This is just more for connecting to things I've seen in other talks on tensor categories. So in your proof of the equivalence of the Picard group and the automorphism, braided automorphisms, you have these isomorphisms from B into the endomorphisms of
Yes.
N. This is just alpha induction.
This is what it is.
Okay.
Yes, that's what
Yes.
it's called. That's why I call them alphas.
Okay.
Yes. Yeah, this is an old thing. I mean, they were studied by Kawahiashi and co-authors like 20 years ago at least. Yeah.
And then another one, completely different question, but with when it comes to like classifying these tensor structures, if you're in the modular case and you have things like, the objects are fixed, the fusion product with the tensor product is fixed, and like the action of the modular group, you've got your S and T matrices. How hard is this to then find, or is this at all realistic? Is this something that's done?
I think Julia is involved in some of these activities.
So
I
I
can't
guess I
tell if
can
it's
ask you.
hard or not. I think it's very hard.
Okay, very hard.
Yeah. Yes and no, but I mean, so S matrix of a modular category gives you kind of more or less the fusion rules of the category. The T matrix kind of does additional thing. I think it's known that you cannot recover the group by this data. There are counterexamples by Schauenburg, right? I think, and others, right? What exactly can you do? It's not so clear to me,
Because the reason why I ask is I always think of this from a vertex algebras perspective. And the vertex algebra has, in the rational case, has easy access to the modular group and has less easy access to the tensor product. But if you have the modular group, you get the tensor product with the S matrix. But things like associators are almost impossible to access. And so if you had some nice way of getting, and braiding is normally also fairly easy. It's normally associators that are really hard. And so if you had some nice way to get associators from the other categorical data.
Yeah, I see what you mean. But however, here we produce a new associator, but we do this kind of in a very cheap way. We start with a grading, and use this. And then who knows? There can be some other associators that do not appear in this way. Right. And then we are probably in the same value situation as you, we don't have access.
Because the VOAs, they pick out a class, a cohomology class of associators. And it's in general, it's very hard to actually get this.
Yeah, that's right. Yeah, I think it's still hard no matter how you look at it.
You have to solve incredibly hard differential equations that you can't actually write down.
You can write them down.
No, I mean, here, like algebraically, you will be doing like the systems of 6J symbols, which is just, I think it's just equally hard as this equation. What one can hope for is that if your category kind of is particularly nice, so for instance, your fusion rules are such that there are no multiplicities, right? Then something can be said in general. But that's it, I think.
If you have the default cohomology group to be non-trivial, do you know there is no extension possible of D as a G extension?
No, I mean, the group can be non-trivial, but whether this abstraction vanishes or not depends. There is a kind of certain map that produces an element here, right?
Yeah, but suppose it's not trivial.
Yes.
Then, I mean, this technique doesn't work. You cannot get a G extension of D. Do you know there is no possible G extension, or?
Do I know situations when this doesn't vanish? Yeah, there are such things. Yes,
there are extensions.
Yeah, at least it's my understanding that all possible like elements of the group can occur. Like in different situations. So this is kind of a typical situation. It's just like, it's easy to talk about things that we can construct than those that we cannot, right?
All right. If there's no questions, I call morning tea.
All right.
See you back at 11.